Today in class we extended our understanding of classifying or naming two-dimensional polygons to three-dimensional solids, which can be many things, but largely we'll focus on polyhedra, plural, which are three-dimensional solids that are made up of polygons. In other words, each face of the polyhedron is a polygon in itself. So if you look at this polyhedron, you can focus on this bottom face. Looks like it might be a square or a rectangle. This face in the front, on the right side here, is probably a rectangle. This face in the front has it's quadrilateral. It has one pair of parallel sides. Mark those. This side is, I shouldn't say sides anymore, I should say edges if it's three-dimensional. So where the faces meet, you have an edge. And so since these two edges are parallel, if we're just focusing on the two-dimensional face, these sides are parallel. And since a quadrilateral with exactly one pair of parallel sides is a trapezoid. And so you have to, I have an example here. It's kind of hard for me to tell. I can't see the camera when I'm doing this, but I think you can probably see that this napkin box has a trapezoid on this face, and on the opposite face a congruent trapezoid. And since those trapezoids are parallel and congruent, they are the bases of this prism. All the other faces are rectangles. And so if you have a three-dimensional solid, a polyhedron with one pair of parallel and congruent bases, one pair of opposite faces that are both parallel and congruent, then you have a prism. If you have only one base, you have a pyramid. And so since we have two bases, I'm going to highlight them here in yellow, just sort of showing that I'm talking about this face. I forgot I have to go slowly for this to work. If I'm talking about this face and this back face as my parallel and congruent bases, well, since these faces are themselves trapezoids, then we have a prism, and it's a trapezoidal prism. So the name of this polyhedron would be trapezoidal prism. Prism, first and foremost, because it has exactly one pair of, I shouldn't say it that way because there are other prisms that have more than one pair, but it has to have at least one pair of parallel and congruent bases to be a prism, and it certainly does. These two trapezoids are both parallel and congruent. And then you name the prism based on the shape of that base, and since the base is a trapezoid, it's a trapezoidal prism. Why don't you, during the pause, try to count how many faces, edges, and vertices you have in this trapezoidal prism, and then substitute those values into Euler's formula to confirm that you've counted them correctly. And you can check your work when you come back from the break, from the pause.
Paused.
I remember that the two bases are also considered faces, so I have two faces, the faces that I've highlighted already, plus 1, 2, 3, 4 more faces connecting those two bases. So I have 2 plus 4 or 6 faces altogether. The edges, I have 4 edges on each of these trapezoids, so that's 8 so far, and then I need 4 more to connect them. So that's 8 and 4 for 12, a total of 12 edges. The vertices are the corners, just like in 2 dimensions, but they'll be the intersection of the edges. And so wherever these edges intersect, I have 1, 2, 3, 4 vertices on this trapezoid, and on this back trapezoid I have 4 more, and that's it. Those are all of the points where the edges meet or intersect. And so there's a total of 8 vertices. If you substitute these values into Euler's formula, you have 6 minus 12 plus 8 should equal 2 if we counted correctly. 6 minus 12 is negative 6. Plus 8 equals 2, and negative 6 plus 8 is 2. So 2 equals 2. We see the reflexive property, and we know we have the correct count on each one of these. Okay, let's look at problem 20. Identify the three-dimensional figure that is formed by each of the nets below. So this one could be kind of tough. I think of all of them, this one might be the toughest one. You have to sort of recognize that this face and this face, when these are folded up, if you imagine these three rectangles folded up, and then these two rectangles folded over, these two bases, these two pentagons, will be parallel to each other, and you can see by inspection that they're congruent. And so, if you have a pair of parallel and congruent bases, you have a prism, and so it's a prism. And then the name of the prism is the name of the shape of the base, and the base is a pentagon, so it's a pentagonal prism. I have one here. Hopefully you can see that okay. And so if all of those rectangles are folded over, then the two pentagons are equidistant at all points, since the rectangles are all congruent, and that's why the pentagonal faces are parallel to each other.